Well, thank you for the invitation. Actually, I'm scientific director of Valeo.ai, not the all AI activity of Valeo. Valeo is a big automotive supplier, very large corporation, French one, but based in the all around the planet. I will say a few more words about the team itself. The main topic of this presentation today is to give an overview of some challenges related to driverless vehicles, and in particular, some of the researches that we conduct in my team towards this challenge. But to start, I'd like to take you for a short ride in the streets of Paris. It was before the COVID, almost already more than 1 year ago, so with normal traffic. And what you are going to see when I start the video is a view of this prototype called Drive for You, which has been built by the driving assistance research team of Valeo. And you will see on the left the cabin view, on the top, on the bottom right, the back of the car, and on the top right, the technical view with 3D positioning, and I will explain going along. But one more thing before I start. This car, which is an experimental vehicle, has the specificity of being built around Valeo sensors, which are already mass-produced automotive-grade sensors. So they are sold and used in current cars. And you see them on the top left. There is 12 ultrasonic sensors, 8 LiDARs, laser scanners, 4 radars, 1 frontal camera, and 4 fisheye surround cameras. So let's start the ride. And hopefully you should see the video now. First example where the car is handling a motorbike, which is overtaking, now changing lane and overtaking another car. What you see on the top right is in blue is the 3D model of the neighborhood, and in red it is the 3 points which are used to localize and register the car in the environment. Now handling a bicycle. So this is another view where you see the 3D. Briefly, you saw the 3D detections of objects in the fisheye cameras. Stopping at a traffic light, etc. Now giving way to pedestrians, which is a good thing to do. Again, these technical views that I mentioned before, and just to finish, going underground with a drastic change of illumination. So you can find the video on YouTube. There is the link. But this gives you an idea of where we were standing at Valeo a bit more than 1 year ago. And the reason why there are so many people working towards autonomous driving, it's because of a number of promises. The first one, the obvious one, is safety. The number of people getting killed on car accidents over the world is just insane. 2 years ago or 3 years ago, it was 1.4 million people around the planet, which is just unbearable. But it's not only about safety, it's also about getting better mobility in terms of efficiency, also energy, saving on energies, and also in terms of giving better access or better mobility to people who are currently devoid, like people, handicapped people or elderly. So there are really many aspects to it in order to go for these technologies. But quite obviously, despite all the bold claims in the past years, and even what I just showed to you in a minute ago, we don't quite see these cars or these vehicles yet on our streets. And the reason is, in fact, that the problem is extremely complicated, probably more than we expected in this industry. In a nutshell, a driverless car is essentially a big robot, which is supposed to be autonomous. It is safety critical. It has to run in real time, or the systems have to be real time, and they have to run on embedded hardwares. And last but not least, it interacts with an environment which is completely open, extremely unpredictable, and this is probably one of the big challenges. So if we want to see one day such vehicles, or in particular driven by individuals, the machine learning and artificial intelligence systems, which are at the heart of this technology, have to meet a number of requirements. The first one, which is quite natural, is that it has to be good. The systems have to deliver accurate prediction. They have to be robust to changes in the input. They should be able to generalize well to new conditions or to adapt to these new conditions, especially those that have never been seen at train time. But that's not the end of the story. On top of that, because these vehicles have to be put on roads, they have to be thoroughly validated. Even better, they should be verified in a formal way, and this, which leads to even the notion of certification, which is something which already applies to any vehicles. So there are regulation body certifying the technologies that you have in cars, in particular for safety. But also, in order for these systems to be also accepted by even the customers, they should be to some extent explainable or interpretable. Otherwise, it's going to be hard to convince people to use them in the long run. And final point, which I already mentioned, because it has to the softwares that we are talking about have to run in a car. They run essentially on hardwares which have constraints in terms of compute power, energy consumption, memory, etc. And so everything has to be compatible with these constraints. All right. So in the face of all the challenges, there are many and more actors or players in this space, and we are not yet there. And in my team in particular, we are investigating a number of topics, which I'm just listing here at a course level. So the two first are really related to autonomous systems, similar to what you would have in robotics. There is a lot of sensor fusion, in particular with the cameras, the radar, and the laser scanners. And this fusion in particular aims at understanding in real time how the 3D environment, both in near field and far field around the car, is unfolding, in order for the vehicle to predict, plan, and act accordingly. The three other big topics that I mentioned are even more general. I think they are essentially challenges for AI at large in order to get trustworthy softwares, services, and products. The first one, which I'm going to discuss quite a lot in the rest of the presentation, has to do with having learning mechanisms and supervision in particular, which can scale. So frugality, but also where you can use whatever data you have, you can use it at best for the future performance of your system, which brings to the other question of reliability or trustworthiness. So how to improve the robustness of the system and at the same time to be able to predict the confidence in the prediction, all the way to possible failures. And the last topic, which I already mentioned, which is explainability, which is still a fuzzy concept, but it has to do with interpreting some of the decisions that a subsystem or complete stack takes in the course of its usage. Let me go, in particular regarding safety, let me show already with some illustration a recent work that we've been doing around pedestrians, but more broadly what is called vulnerable road users, so pedestrians, cyclists, etc. So this work, which is conducted with EPFL, has to do with the fine-grained analysis of pedestrians which are seen from the cameras of the car. So what you see for now, which is a true result, is a classic pedestrian detector, which essentially finds bounding boxes around the pedestrians in the scene. And what we produce on top of that, and this is really the result of this work, is the following. We actually analyze 32 different attributes, including the gender, the age, the clothing, whether the person is wearing something, pushing something, even more importantly, whether the person is intending to cross, or is this person attentive, or maybe this person is in fact talking on the mobile phone and it is not very attentive, etc. So what you see on the screen here is an actual result of the system after it's been trained. So just a few words, and I'm not listing obviously all the attributes, but you get the flavor. The way it works in a few words is as follows. So it's what is called a multitask learning system, because there is a single neural network, artificial neural network, which predicts for the 32 attributes what is the value of the attribute. So in the case of the age, it's an age category. In case of some of these attributes are binary, so it's a yes or no output, etc. Everything is the system is fed with one image, and then there are 32 what are called heads, so outputs, if you wish, of the system. So the one of the reasons for doing everything with the same neural network is that you can share a lot of the encoding. In particular, most of the network is shared by all the tasks, which means that effectively you factorize the most of the computing, which is important for embedded systems. And another aspect, which is on the training side, is that you can leverage the fact that you have annotations for different tasks possibly on different data, so you can really transfer the knowledge from one task to another. In terms of architecture, it's based on the system from last year, from 2019, sorry, which is called PIFPAF for person detection, and which is based on what is called the composite field. And effectively, what the neural network regress is a field of scalars or vectors, and in each cell of at the image level, each cell of the prediction tells you whether there is a pedestrian in this cell and what are the attributes, etc. So it's a structured, what is called a structured output prediction, which tells you about tentatively about all the pedestrians in the scene, and for each of them, what are the attributes. And in terms of training, because it's to my knowledge, it's the most extreme multitask learning system in the literature, with so many tasks. For those who are familiar with the training of a neural network, when you backpropagate at training time, you have these 32 heads sending signals back to the encoder of the system. So you have a very delicate issue with balancing the different gradients coming from the different heads, and this is one of the contribution of this work. And we managed to do that also because there is a very interesting data set which is freely available, which is called JAD, and you have the reference on the slide. Another earlier version, or a slightly different version of this work that we did previously, and which was demoed 1 year ago exactly at the CES in Las Vegas, is the following. So in this case, you see actually there are fewer attributes, but you see as well the pose of the person, which is estimated at the same time. And you can imagine that this level of analysis of the pedestrians can be then turned into better understanding of the scene and safer driving for the autonomous vehicle. Okay, let me switch to probably what is one of the key topic of my talk today, which has to do with the data we have for the perception of the autonomous systems and the way we do supervision. As per now, the best-in-class perception models that you see in the literature, whatever the application domain, is based on what is called fully supervised learning, which means that you have to provide input data and ground truth output in order to train your system. So this poses different challenges. The first one is that already collecting data for the applications we are interested in can be quite time-consuming, even sometimes dangerous, because of if you really want to have problematic situations in your data. And this is just for the raw data, so just recording the images, the LiDAR point clouds, the radar signals, etc. And then you are back to the lab or to your premises, and you have to annotate. And annotation, which is to specify the ground truth for the task at hand can be a real nightmare. Even though in some cases it's not possible to do that by hand. I'm taking, for instance, the very important example of depth estimation, which is that for each pixel, you need to specify the distance from the physical point to the camera. So obviously no human being can do that. So we need other ways to accommodate this problem. But so this is a numerical information because it's really a distance. But even if we stay with the semantic information, which is what the humans are better at, it can be very difficult. So let me take this example, which is very emblematic, which is the task is called semantic segmentation, and it's one of the perception tasks that we have in our vehicles with the cameras, but we do that as well with the point clouds. So in the case of the image, the task is to guess what is the semantic class of each pixel. So whether it's street, pavement, pedestrian, sign, trees, whatever. And in order to train a model to do that, you need to have this type of ground truth annotation. So these two images are taken from cityscapes, which is a very important data set in the community. And the annotation by humans has taken more, I think, more than 1 hour per image, and it's probably $1 or so in terms of cost. So if you want to do that on millions of images, it clearly doesn't scale up. And even if you can afford that, my view on that is that it's never enough anyway, because when the system is deployed, it will face anyway new situations, especially over the lifespan of a car, which is 10, 15 years. So even this sort of brute force supervised learning approach to learning such systems is probably is certainly not sufficient. Still, there are plenty of interesting data sets, which is really precious for the whole community. It all started seriously in 2008. So over the decade, there were quite a few. Some are very popular, in particular Kitty and Cityscapes. But what is remarkable is that if you look at what happened in the past 2 years, and this list is not even exhaustive, I think, there has been a surge of many new driving data sets with videos, point clouds, localization of the car, etc. And the other interesting remark here is that this is the meaning of the purple color code, is that many of these data sets have been totally or partially put together by industrial players, including ourselves. So this is really good. I think that all the private companies are also contributing to this data sharing effort. And to complete this picture about data set, it's important also, I'll get back to that a bit later, that there are also synthetic data sets, which are very handy because you can script yourself the situations, including very difficult one, and all the annotation in this case is for free. Starting with semantic segmentation, you don't need to ask humans to annotate real images. And you can train on massive amount of synthetic data. But of course, it comes with challenges that we are going to discuss a bit. So as I said, full supervised learning is very powerful, but has a number of limitations. And fortunately, there are many other alternative ways of supervising the training of machine learning models and artificial neural networks in particular. So this is a long list. I'm just going to stop and look at a few keywords and connection between those. So the two first, semi-supervised and weakly supervised, this is the situation where you train with only part of the annotation, either because some of the data are not annotated at all, or in the first case, and the second case, everything is annotated, but not to the extent of what you need for your task at hand. More radical, self-supervised and supervised learning, there is no annotation at all. So you just have raw data. So in that case, you cannot quite go to the semantic level, but you learn useful representations. very powerful nowadays and popular. Zero-shot learning and few-shot learning, you learn, in particular for recognition, it's about learning from either a zero example at all or just a few, but of course you need this dramatic lack of data is compensated by other types of knowledge that I will maybe mention later. And a big topic, even central to many of these things, is transfer learning. So transfer learning is learning on a different task or learning on different type of data or in a different domain, and then use that or reuse that for new task, new domain, etc. So it's already also about making the best use of whatever training data you have, at least when it is related to your final downstream task, and it's a very broad concept, and it goes into different forms. For instance, few-shot learning, zero-shot learning, multitask learning, domain adaptation that I'm going to talk about after, and also learning from synthetic data are all forms of transfer learning. For instance, in the case of multitask learning that I mentioned with the analysis of the pedestrians, the different tasks which are trained together, effectively they share knowledge, which means that they exchange effectively knowledge. So it's a form of transfer learning, etc. Conversely, some of the tools in this list can be used to produce transfer learning. So, for instance, I just say that self-supervised learning and unsupervised learning allows to learn useful representation from unlabeled data. Well, these representations, if they are reused down the later to train effectively for a given task, then it's an effective transfer from unsupervised to a supervised task. Another interesting example is distillation. So distillation is training one neural network or one machine learning model under the supervision of annotation, which are typically human input, but also under the supervision of another neural network which has been trained differently, which is called the teacher. So it's called teacher-student distillation, and this is a very powerful way to transfer knowledge. Another remark is that I want to make on this list is that many of these alternative supervisions, they can be combined. For instance, in a recent work, we showed that self-supervised learning, which is how to learn representations from a fictitious task that you can easily make up and supervise by itself, can be very useful when you do few-shot learning, which is say learning to recognize object categories from 1 or 5 examples only. Another interesting connection is when you do active learning. Active learning is the task of learning from a large set of data, which is only a fraction is annotated at the beginning, and through several phases you annotate more and more. Hopefully, the more useful in order to get better model. But effectively, at each step of active learning, you have one part of the data which is annotated, the other one which is not. So it's effectively a semi-supervised learning setup. And the last one that I want to mention is self-training. So self-training, which I will mention also a bit later, is the fact that you can use an already trained model to produce automatic annotation, and this can be combined with semi-supervised learning, active learning, and domain adaptation, as we will see in examples. So one thing I want to now focus on is domain adaptation. So domain adaptation is related to the problem of training on data which are typically acquired in certain conditions, and then to be able to run the system in different conditions. So we talk about source domain and target domain. In this case, the source domain is sunny weather, the target domain is winter situations, but also it could the domain gap could be due to elimination, typically in daytime versus nighttime. It can be also because of the geography. The training data are taken in certain regions of the world, and you want to be able to deploy everywhere, maybe. Last but not least, it can be also that you train with certain types of sensors, like a classic camera, and you want to deploy on fisheye cameras. This is pretty drastic change. And the last one, which is very important, already mentioned previously, which is training from synthetic images, like game engine, actually, which is very easy to control. So the source domain is synthetic data, and the target domain is the real data. And in particular, if you do that for the semantic segmentation task, which I described earlier, if you train on synthetic images with ground truth, and then you run your train model on a new synthetic image, then you can get this, which is quite satisfactory. But if you run the same model on a real image without any fine-tuning or changes, this is what you get, which is a mess. And this is really due, so this you end up with a big drop of performance due to this domain gap between synthetic and real images. And this is the setup I'm going to discuss a bit now. Again, source domain is annotated synthetic images in this case, and target domain is unlabeled, is real data, is real scenes. And now we assume that at training time, we have nonetheless sample images from the target domain. They are not annotated, but we have true scenes. So we have synthetic scene annotated, true scenes not annotated, and we want to make the best out of that. So this is a very active field of research. I'm just illustrating here with work we did last year, which is based on what is called entropy alignment. So let me explain briefly at least the highlights. So you train, so you have already a model that you know which is good at doing semantic segmentation. It's a convolutional neural network, and you train it on your annotated synthetic images, as we saw. And if you do nothing else, so it goes well on other synthetic images and badly on real images. So the point here is how to now leverage the knowledge of true images, even without annotation, at train time to do better. And the idea that we explored in this work is to look at the confusion or the uncertainty or certain idea of the uncertainty of the prediction at the pixel level of the train model. So if we look, so the neural network, you have to understand that each pixel it doesn't only predict a class. Effectively, it predicts let's say a probability or a score for each of the different classes. So if you have in this case 6 classes, this is the meaning of the I don't know if you see my mouse here, of these 6 color panes. It means that for each class, at each pixel, you have a score, and you can see that as a distribution and compute the entropy. So at each pixel, you can compute an entropy, and this is what you see here at the bottom, associated to the segmentation of this synthetic scene. So it's pretty confident, low entropy, except at either at the border of between regions or far away, where the resolution is very small. And again, if we compute that for on the real scene with the current model, we see that there is a lot of uncertainty all over the place. The hotter the color, the higher the entropy. And the idea is to train now or continue training the model by trying to minimize this entropy on the source, on the target domain images, in order then to get this type of improved confidence, and then as a consequence, better decision. So how it works, I'm not going to go through the notations, etc., but just to give you an idea of this type of domain adaptation, unsupervised domain adaptation techniques. So at train time, you have both target and source images. If the image is from the source, so it comes with the ground truth semantic map, so you can use the classic supervised loss to on this pair on this image. But if the image comes from the target domain, you don't have the ground truth, but you can compute at each pixel the class-wise entropy, and we can have a loss which minimizes or tries to make this entropy as small as possible. For that, you don't need the ground truth. You just look at the distribution of the scores at each pixel, and so you have multiple losses. And it's also very importantly, it's an adversarial approach, means that also at training time, you could train another network, which is called a discriminator, and which role is to try to distinguish between source, just looking almost at the output of the network, whether it was seeing a target domain image or a source domain image. And the idea is that by trying to fool this discriminator, the main network will learn more and more domain agnostic features in order to get in order to provide or to predict the class at the pixel level. So it's a fairly classic thing. All the details or the novelty is where to put the supervision, and whether it's at the beginning, the middle, or the end of the network. So just results here. Maybe just with the video, it's better. So you will see what you will see on the bottom left is without updatation, bottom right is without the method we propose, and the image-in-image heat map is the uncertainty, or in the sense of the entropy at the pixel level. And you see that the improvements are quite visible. I mean, there are still plenty of issues, and so lots of margin for improvement. And in the past 18 months, there has been already a number of other works improving on that in the community. But you see visually, at least qualitatively, you get the idea. For the now maybe I can talk about this one. So a follow-up project that we had on the same year illustrates another interesting idea or concept from the machine learning community, which is called learning using privileged information. So it's effectively the idea that at train time, you might have access to additional information more than what you would need at runtime, in particular in the case where the data is synthetic, in our case here. And instead of learning how to segment these images, you can learn more. You can also learn it, then it becomes a multitask learning problem. You can learn at the same time to predict the depth map. This is exactly what we did. And by learning a network which does the two things at the same time, there is an actual transfer between the two tasks, and the semantic segmentation stream can benefit from the quote-unquote understanding that the network requires to predict the depth. And this, combined with domain adaptation, brings new improvements. In this example, you see in the maybe in the little yellow box, you see that the cyclist is better delineated. So this is not massive improvement, but interestingly enough, it does better on fairly interesting or important classes like cyclists or pedestrians. But of course, it does require, it wouldn't work with training data or source domain, which is not synthetic, because in that case, you wouldn't enjoy the fact that you have depth map as ground truth. I'm not going to give more detail about the architecture, but hopefully you get the idea. And these are examples where you see on the last column some of the gains that we get compared to the other work that I presented just before. The second column is the ground truth, and again you see that it's not. I mean, at least there are some improvements quite visible, in particular again on the small objects. I'm going to skip that for the sake of time, and I'd like to talk about another concept which we use actually for the domain adaptation, which is self-training and pseudo-labeling. So self-training, I already introduced it before very briefly. So that's the idea that you have some data which is partially annotated, and you can already learn a previous current model and use this current model to label the rest of the data, and these labels are called pseudo label. So it's an automatic annotation of the other data, and you can retrain your model with this new annotated data. So, and it's been introduced in particular for semi-supervised learning for obvious reasons. But the issue, of course, is that especially at the beginning, the prediction on the unannotated training data might be extremely noisy. So if you take them for granted as ground truth, then and you use that to retrain the model, it might be bad and even diverge. So what is very, very important is to only select some of these automatic annotations, at least those for which we have a good sense that they are that they might be correct. So we need to have some idea of the confidence of the current model on this data. And one thing that we did a lot is to use that. So as I said, it's very popular and very well known in semi-supervised learning. We use that for unsupervised domain adaptation. Um, and now I'm going to talk about a few ways to estimate the confidence. So still for the same task of semantic segmentation of visual scenes, but what I'm going to mention here could be for other tasks. So if you have a model that do semantic segmentation at the pixel level, and you want to predict what is the level of confidence or what is the uncertainty associated to each individual decision at each pixel, one thing that we already leverage when I mention entropy is to look at the distribution. So in this case, imagine that you have and if it's really peaky around the maximum score class, the network is fairly confident, which of course doesn't mean that it is right. It can be very confident and completely wrong, but that's part of the game. In any case, well, there is an even simpler way to estimate the confidence is just to look even at the score of the maximum score class, which is the one that you are going to select as the predicted class. In this case, is the green bar. So you just look at this score, and if it's above a threshold, you declare that the decision is very confident. And for our problem of pseudo labeling, you can retain this label for this pixel in this scene to be reused later on as a training material. And this is what you get. As I said, already a more sophisticated way to go about it is to look at the actual distribution, and if it's very peaky, so it's essentially the threshold is now on the entropy. So the lower the entropy, the more confidence, at least as a prediction, and then you retain only pixels which corresponds to low entropy. If the entropy is too high, it means that there is a lot of confusion. And already doing that, we showed that many wrong labels are, well, many, at least a number of wrong labels are avoided this way. And it's not very easy to see on the screen. You will see that on the slides that I will share later. This shows all the pixels which pass, which are different, which pass one test and not the other one. And in particular, there are a number of pixels which don't pass the second test, which are effectively incorrect labels. So this is very important. So we get better quality pseudo labels. A last way a third way to estimate the confidence is based on works that we started in 19, where instead of looking at the maximum score class or the spread of the distribution, we are going to try and predict with another model what is the actual uncertainty of the main model. So it looks like that at a very high level. So you have a segmentation model which is already trained, all right, and it does predict semantic label. So this is the bottom stream, and we are going for this model. We are on top of this model. We are going to learn another model whose task is to predict at each pixel what is the score of the true class. So of course you can do that at train time, if at least for the data which are fully annotated, you know the true class, there is a ground truth, and so you know what is the score for this class as per the predictor, and you learn this auxiliary model in order to predict this true class. And this is what we did here. And it turns out that the pseudo labels we get are even better compared to what I showed previously with the entropy. What time is it? So I'm going to skip just a few things. So the basic idea, just for the reference, and there will be a list of references at the end anyway. So the main idea was not, we did it in 19 at New Rips, not for semantic segmentation, but for image classification. But it's exactly the same concept. All right, let's see. Okay, so oops. I will finish just with some more illustrations of follow-up works that we did, and still around this idea of alternative supervisions or limited supervision. So this is a work also that we published at New Rips, where we attempted to do zero-shot semantic segmentation. So zero-shot learning is the problem of recognizing new classes for which you have no examples at all, but you have already a model trained on other classes, and you know this, to some extent, the relationship between the new classes and the base classes for which you have already trained with examples. So the relationship between in form of attributes or some type of knowledge. So in this case, we have a, I'm not going to give the details, but we have a semantic, it's in the paper, we have a semantic space where we can map different semantic categories, and we see proximity. So a new class can be related in this space with older classes for which we have actual examples. So, but just to give you a sneak preview of the results, so these are 3 examples for which we see before and after. So first example with the motorbike, the model doesn't know about motorbike, and now he knows about other classes like bikes, but not the motorbike, and now we can in a sense adapt it in order to recognize motorbike pixels, although he has never seen any, and this is what we get. Second example, where the new class is a cow, and at the beginning essentially the cow is seen as mostly as a horse, and then with the zero-shot approach, we are able to recover most of the cow pixels as such. And last example for the train. So the first labeling is as truck, and then we recover the actual train segmentation. And the last example, and then I will stop after that. The last example work is an extension of the previous one. So it's the same problem, but on top of that, the new classes that for which you have no example annotated, on top of that, from a different domain. For instance, you have a semantic segmentation model which is trained on European cities, and then you want to have this model able to recognize specific vehicles in Indian streets for which it has never seen annotated examples. And this is what you see here. So you see first column example images from the Indian driving data set, then the ground truth, then the output of the methods I just mentioned before, which fails in particular on the tuk-tuk, these very specific vehicles that we don't see really in the cities of Germany or France. And you see the last column, which is the result of what we did in this work, which is currently under submission. And with that, just to leave a bit of time for discussion, I will just jump to a little family photo with all the team members and the names, the mention of our academic collaborators, at least their labs and affiliations, and you can find all this information on our webpage. And this is the list of the works I mentioned, where on top of that you can find, of course, the discussion of the state of the art and that I didn't mention in my presentation. And with this, I can stop and take some time for questions and discussions. Thank you.
Thank you very much, Patrick. And you presented the algorithm for the segmentation, but do you run tracking algorithms such as particle filter, as we have seen in the presentation of this morning, or for the tracking?
Okay. Yes, for tracking, a topic which is very close to my heart. Actually, at the 20 years ago, I did work, including with Arno, on particle filters. So we, in my team at the moment, we don't work explicitly on tracking, which is certainly something very important. The other team, the one which did this fantastic experimental car that I showed at the very beginning of the video, there is obviously some tracking. So once you have the, but it's, I believe it's a fairly simple one as per now, for a number of reasons, in part, including compute power. So there is the 2D and 3D object detection at the instantaneous, at each instant, and then you link these detection through time in order to get small track or tracklets, and then this allows you to do some prediction. This prediction can be indeed done with particle filters, in which case you get the distributions of the future states, and then you can update that when you have new evidence. And this is the prediction phase, which is key before doing the planning for your vehicle, and then the actual action to realize this the plan. To really go along the planned trajectory. It's more generally one thing that we started to look at, and as a number of other teams in the field, is more generally what is called forecast. So predicting, so which is the beginning of tracking, as you probably saw with Arno. You need to predict before updating your filtering distribution. So the idea in particular is to predict really in real time the action, trajectory and action of all the road users, cars, well, vehicles and pedestrians in particular. And one of the difficulty actually is to do that, to predict multiple possible futures, which is exactly one thing that particle filter can do. But it's so people at the moment are playing with different ways, including particle filter, but it could be other machine learning tools in order to predict multiple futures. One of the challenges here is the supervision. For one thing, okay, already having tracking ground truth at scale is very difficult. So in the long list of very recent data sets that I mentioned, just a few of them have it. I think the Waymo open data set, they have now the tracking for, at least for the vehicles, because in terms of annotation, it's way more demanding. You need to do that on every frame, and you have to maintain this temporal link, so it's way more demanding. So this is already one challenges we have in terms of supervision, so supervised learning, for which you need annotation. And it's even more so if you want to learn how to predict multiple possible displacement, which makes sense, because obviously even if you annotate, you have only one trajectory in the annotation. You don't have multiple trajectories. So one way to go about it is to actually, again, to leverage synthetic data. So virtual environment in which you can replay different scenarios starting from the same instant.
Okay, thank you. And do you train the model for each car, or
no, of course not.
That you use
No, of course
every
not. Yeah. But okay, well, I say of course not, but that's not so easy. So first of all, we as a company, we don't sell cars, we don't deploy cars, so we have a small number of experimental prototypes which run the same software. So we train with data which are collected with several recording cars, and then we train the models, and then the same model is deployed on all the platforms we have, except when we have extreme geographic differences. So we have prototypes in Europe, we have prototypes in Asia, we have prototypes in the US, and there are, as far as I remember, there are different. Well, there are obvious differences in the subsequent modules of the driving stack, just because the driving rules are not all the same. In the US, the way crossings are handled is different, but it's also already the case with the perception. So even if the rules are the same, in the US, again, the traffic light is not at the same position. Quite often, it's after the crossing, which is, as a human driver, I found pretty disturbing myself when I did my postdoc there. Anyway, so there are different things. There are some differences. Some are quite subtle. Some are quite obvious, like traffic rules. So the four-way stops in the US or in Japan, they drive on the other side of the road, like in England, etc., etc. So we do a bit of at the moment of adaptation without the tools that I mentioned, which are research tools for now. But it's one of the reasons we want to do domain adaptation, which is not to retrain everything from scratch. But just a final point on that: if you now imagine an actual a car which is actually sold, like but typically the obvious example is a Tesla. So Tesla, they have fairly sophisticated driving assistance systems they call autopilot, which uses a lot of these things like machine learning for perception and decision. All the cars, they have the same software, but it can be upgraded like for mobile phones. So you have what is called over-the-air upgrade of your software. But I doubt that I really doubt the software is different from one car to another. Otherwise, it becomes extremely difficult to maintain, to guarantee the safety, etc. So yeah, I'm pretty much sure that it's exactly the same software at least on the same car model across the customers.
Okay, thank you very much.